Good afternoon, everyone. I'm pleased to introduce our speaker today, who is Dan Scheeres. I've known Dan for about an hour. So as a consequence, I've been chosen to introduce him. But Dan is he's a distinguished professor of aerospace engineering. Distinguished professor honor is given, it's a system-wide honor. And he holds the Dick Seabass Chair of Aerospace Engineering. Dan received his PhD from the University of Michigan and then moved on to JPL for 5 years and then took a faculty position at Iowa State before moving to University of Michigan, where he held his next faculty position. That was his home department. He received his PhD from them sometime earlier. In 2008, I believe, Dan came here to the University of Colorado and has since been elected to the National Academy of Engineering in 2017, and has had an asteroid named after him. You might know this, Mike Dubson. It's asteroid 8887. That's the Scheeres asteroid. Okay, so Dan has particular expertise in the nature, dynamics, and evolution of small objects that are in strongly perturbed orbits. And he's going to be talking today about the collapse and ejection of the in-body problem and the formation of Rubble spiral asteroids. Welcome, Dick.
Thanks very much, Mike. Hopefully that sounds okay. Yeah, thanks for the invite to come and talk to you a little bit about some of the work that we have going on. I sort of picked a particular topic because I wanted to see if physics people would think it's interesting or not. So we'll see how that goes. Since I am like next door, I thought I would do a very quick intro to my lab, which I started up when I showed up here like 15 or so years ago. And the sort of work that we do actually covers a couple of different areas. Space domain awareness, which is what's going on in the Earth-Moon system, which really means what's going on with artificial satellites in the Earth-Moon system. I've been very involved with asteroid and planetary science, been on a number of missions and have led some. And then my background really is more in celestial mechanics, astrodynamics. And these are the techniques I bring to the different areas that I'm studying. And really what I'm going to talk about today is more in the celestial mechanics domain, just because I thought this is a great opportunity to talk about that. So, thanks. Ultimately, the talk is going to be focused on asteroids. And I think it's always important to sort of cue this up. You know, what's the big deal about asteroids, the little rocks in the solar system? They're not nearly as big as the planets and all that. And really, there are 4 fundamental reasons why we have and why NASA has a pretty big focus on the study of asteroids. The first is the scientific answers, or really the scientific driving questions to understand these bodies. Because these asteroids, and I would actually put in other primitive bodies like comets, Kuiper Belt objects, and the like, are really the remnants of the early solar system. So they go back to the formation of the solar system. And at some level, they also act as almost like tracer particles in the solar system that actually document how the larger planets have actually evolved over time. They've shaped life on Earth, delivering water and minerals to the early Earth, occasionally cause big impact extinctions that the last one we've benefited from. And they're also interesting as sort of a unique form of matter. Because when you get these very small bodies, the gravitational forces, the inertial forces, and even like the van der Waals forces between grains are sort of at the same level. And the study of matter in this state is a bit unique, and it relates to many other environments in the solar system, such as planetary rings, protoplanetary disks, and other sort of extreme types of matter. So by studying asteroids, we get to sort of get insight into these mechanical properties. And maybe the most important one is you can get on the cover of Science and even Nature once in a while if you work on asteroids, because there's cool pictures. So this is probably the main driver. There's always this exploration driver out there. People love the idea of going out to asteroids. NASA's actually invested significant money in technology for doing human exploration of asteroids. It's not super popular right now, but it has been in the past, might be in the future as well. So that's a driver. Another big driver we were talking about at lunch are resources. Asteroids have metals, they have minerals, they have a lot of material that could be very useful in outer space. It's not practical to bring any of that material back to the Earth, but if you can process it, use it in outer space, that's a proposition that could make someone some money at some point, probably relatively far in the future. It doesn't stop people from starting up companies. In fact, this one here, Carmen Plus, they moved their operations to the Denver area and are busy working on some prototype missions to go and test out various mining approaches at an asteroid. This earlier one, Planetary Resources, had a very detailed and complete plan for how they were going to actually monetize it, except they've been bankrupt now for about 5 years. So it's a tough market, I think, but at some point something's going to happen here. Ultimately, probably one of the main reasons why we really do want to understand these bodies is really from a social perspective, because they do hit the Earth on occasion. It could be 10,000 years before there's a big one that hits the Earth again, but it could be much less than that. And it's something that NASA and the world community is definitely focused on. And in fact, NASA just had this first planetary defense mission that struck the asteroid and actually gave it some impulse in a measurable sense in order to test out some deflection technologies. And that was just 1.5 years ago that happened. So those are the sort of the drivers for why asteroids are of interest to us scientifically and socially, I think. So with that as sort of queuing things up, the current question that I'm going to talk about and sort of give some of an overview of the work that I've been doing over the last decade or two is the basic, very interesting question of how do these rubble pile asteroids form? If you take a look at a small asteroid, Itokawa, this is about the size of the Empire State Building. If you just look at it, it's immediately clear to you that this is just a collection of rocks resting on each other, right? You don't see anything, substrata or anything like that. It just looks like a pile of rocks. And in fact, we've looked at a number of different asteroids, and they do look like that, but there are some key commonalities that we find. Several of these asteroids are actually of completely different types, completely different mineralogy, density, and everything else, but they evolved to very similar looking shapes. So there's a question there. Why do these very disparate materials drive themselves to a similar shape? And for that, we believe it's probably a mechanical process that goes on, something that we'd like to understand better. And also, with the recent OSIRIS-REx mission, we were actually able to determine pretty precisely that the distribution of material inside of these objects is not uniform. So in some sense, it's not just a pile of rocks. It actually has some structure and some interior structure. And the work that we've been working on here is we're trying to understand how these guys come together and form, how they evolve over time, what sort of mechanisms are driving this whole process. And that's sort of an interesting, very fundamental physics type of question, or celestial mechanics type of question. So maybe a little more detailed question is, what sort of celestial mechanics constraints exist for a collection of self-gravitating grains, like we have depicted here? And we do see that we get this pretty wide variety of shapes that can occur. Single asteroids, binary asteroids. Some of them are in very stable configurations. Some of them are in very excited, turbulent configurations. And we want to understand sort of the totality of all of this. The physics boils down to mechanics because the forces involved are tiny. So if you have these two rocks resting on each other, their gravitational attraction is not big enough to actually compress these two bodies. We have to get up to 500, 1,000 kilometer sized bodies before they start to pull themselves into a sphere. And we're way down on that food chain, generally looking at bodies that are less than 10 kilometers down to even a few hundred meters across. So the way we generally address this problem, which I'll call finite density celestial mechanics, for a reason that I'll show you in a second, is one very common way of addressing this is numerically. We can take a lot of grains, we can collect them in a pile, we can rotate them, and then we can observe what sort of behaviors occur. All of these simulations can take quite a while to run, and as a numerical simulation, it's hard to draw any first principles out of this process sometimes. We're basically coding up first principles, seeing what happens, and we're trying to interpret what comes out of it. What we're trying to do with this work is to take a step back and have a more analytical approach to constrain what sort of relationships exist between configuration, angular momentum, and energy. So at this level, what we can say is, well, we should conserve angular momentum, and we can dissipate energy. And beyond that, it's just sort of a run of the, a roll of the dice in terms of what dynamics ensues and what sort of behavior we see. So we'd like to get a little more systematic than this. And the approach that we've taken is ultimately quite simple. And it turns out that just by studying this one function, what we can call the amended potential, and the way we're using it, we're sort of using it as a minimum energy function. Through the study of this function, we can actually come up with a lot of very strong constraints on how a system of particles resting on each other, what sort of shape, what sort of configuration that they can form and be stable. We can also come up with constraints on ejection of particles. What does it take to eject a particle? How much energy do you need before you can start losing particles? And that's what I'm going to really walk through in the next, for the rest of the talk, is different ways that we've used and analyzed these finite n-body systems using this pretty simple tool of the amended potential. So let's just talk about it for a second. It involves a couple constants. The capital H, total angular momentum of the system. E is the total energy of the system, which nominally is conserved, but as soon as you have any impact, any surface forces, you start to generate friction, so you can actually dissipate energy and drive that down. We also have to specify the system configuration, or the degrees of freedom of our system. And this is really just the minimum number of coordinates needed to specify the system configuration. And we're not going to get too deep into that, but the nicest thing is we don't need to worry about velocities. We just need to worry about relative positions, relative locations when we use this approach. We have a couple functions of the system configuration, coordinates and orientations that can change dynamically. I sub h here is just the system total moment of inertia about the angular momentum direction. It's not the polar moment of inertia, which is used a lot in celestial mechanics. This is, it's a little different. It's actually a little sharper of a result when we use this form. And then this, of course, is just the total gravitational potential energy. And it includes, of course, mutual potentials. It also includes, in general, self-potentials. So it turns out analysis of this single function actually gives us everything about the system's dynamics. We can generate the equations of motion using this guy, the equilibrium states and their stability, limits on when escape can occur and when escape can't occur. So in the formulation that we're taking, we're dealing with rigid bodies in general. We're not dealing with point masses, and that's an important distinction. So when we form the total angular momentum, we have n bodies. We add up their point mass angular momenta, but we also have to include the rigid body angular momentum as well. This is the total moment of inertia about the angular momentum direction. So this h hat is a constant that we deal with, and the body can change its orientation relative to this. As it changes its orientation, moments of inertia increase or decrease, and that has to be compensated, of course, in the total energy and in the total angular momentum. And then the mutual potential, or the gravitational potential, is just the sum of all of the mutual potentials between the bodies. And we can also include the self-potential of each body as well. If we do that, then we can actually account for reshaping of bodies if they're actually subject to, depending on how detailed we get in terms of the stresses and strains that can act on individual bodies. Usually we treat these as rigid bodies, but also when we start making some continuum assumptions, we do have to track the self-potential of the whole system. So the ideal model is we have two non-spherical bodies interacting with each other gravitationally. And since they're finite density, they can also touch and generate surface contact between the bodies. So this is the general formulation. One that's a little simpler to work with is what we call the sphere-restricted full n-body problem. And the only thing we're changing here is we're just saying, hey, instead of an arbitrary shape, we can make these guys finite density spheres. And then it becomes very easy to calculate when they rest on each other and when they don't. The gravitational potential becomes trivial. We can still track their self-potential if we want to. And things become easier, although fundamentally not much actually changes. We just don't need to track there's additional internal degrees of freedom, such as relative orientation, that we don't need to track anymore once we make this assumption. So a lot of the analytical work, we do make this assumption. Okay, so how do we use this amended potential to start studying this system? The first thing we look at is what are the relative equilibria that can exist inside of the system of particles that can rest on each other and gravitationally attract each other. And to find a relative equilibria is if we have the particles in a certain configuration, all we need to do is find where a deviation of that amended potential is greater than or equal to 0 for all possible deviations. If they're not in contact, this guy needs to be 0. If they are in contact, we just have to have that in every way we move the relative degrees of freedom, the energy, the amended potential is going to increase. Once we have these identified, stability is very simple. We just look at the second order variation of this amended potential, and that immediately tells us whether or not it's energetically stable. This doesn't tell us if something is linearly stable, which is the Lagrange points in the three-body problem are an example of a relative equilibrium that can be linearly stable, but in fact, those are not energetically stable. Because if you dissipate energy, those equilibria will actually fall apart. And since we have all these contacts, we're interested in this energetic stability. So we can start counting relative equilibria. When we have two bodies, it's relatively simple. They can either rest on each other or they can orbit each other and in a circular orbit for a relative equilibria. And I bet you all knew that. When we go up to three bodies, it actually starts to get interesting right off the bat. So these three types over here, Lagrange and Euler orbital, are the traditional point mass relative equilibria that can exist in the three-body problem. Nothing else can exist. But as soon as we add this finite density constraint, we actually get all of these additional relative equilibria that pop up. And an interesting aspect of it is that there are many of them that can actually be energetically stable, meaning that if you dissipate energy and if you're close to one of these configurations at the right level of angular momentum, the system will actually settle down into one of these configurations. And in fact, we can go beyond and actually come up with sort of evolution charts. As we increase, say, the angular momentum from 0 to infinity, we can actually track out all possible relative equilibria that bifurcate as we go to higher and higher angular momentas, and also identify all of the different configurations that are stable, the ones that are unstable that we don't necessarily worry about. And you can do all of this analytically. We can move it up to the four-body problem where we start to get a large explosion of different types of relative equilibria. We have single collections. These are static, so any one of these, if you spin it at the right rate, it will just be a happy relative equilibria. We can form binary systems. We can form multiple systems as well. I'm not showing that it's also possible to form three-body collections of particles that would be in a relative equilibria. But it's actually been shown that for n greater than or equal to 3, all of those, independent of whether they're point masses or distributed bodies, will never be relative or energetically stable relative equilibria. So we only will get stable relative equilibria if we can pack everything into one body or everything into two bodies for these finite density situations. So maybe a slightly better way of showing how angular momentum and energy relate to each other is with these charts that actually allow us to map out, as we increase angular momentum for one of these bodies, we can trace out actually what the energies or the embedded potential value of these different relative equilibria are. And we see how they can cross each other. These guys are the formation of orbiting pairs. Some of these are unstable, like the Euler and the Lagrange. Some of these are stable, like this particular, what I call the aligned configuration, or unstable, like this guy over here. We could do this for the three-body problem, for the four-body problem. Again, it gets more and more complicated, and it gets harder and harder to guarantee that you found all of the relative equilibria. But this gives us a pattern that we can start to follow, and we can actually, normalize the energies, put everything on one common chart to just get a feeling for how the energy of the two-body, three-body, four-body problem will change over time. Now, when we have, say, the four-body problem here, this lowest line here actually defines the minimum energy that the system can have at a given angular momentum. And we'll talk a little bit about this later when we start trying to use these to sort of map out how we lose energy in the system and collect in certain shapes and configurations. First, we would like to go up to higher numbers, and we can come up with a sort of a crude approximation. And in fact, we can exactly calculate sort of the highest energy relative equilibria. And you can get these kind of crazy situations that exist for the highest level of angular momentum, where you can just stack up all of these guys in a row. And if you spin them at the right rate, this actually will form a stable relative equilibrium. And we can compute when it becomes stable and when it loses its stability and actually fissions and comes apart. So this allows us to extend, and here we can make an analogy. This is crude. If we have 21 bodies, there are a finite number, but a huge number of different transitions that exist as we go from zero angular momentum up to this maximum. And I don't want to trace them all out, but this gives us a rough rule of thumb for how these systems will evolve for more and more n. And even here, we can sort of trace out some fundamental limits on how much energy, how much angular momentum can be contained in these systems, what the different stability levels are. Just by using, for a large number of particles, we can start making some approximations about how these guys can collect themselves together in minimum energy configurations. Some interesting work that I was just exposed to last year when I was visiting some colleagues in Paris is that there are actually there's a work being done on central configurations. And if anyone ever took a celestial mechanics class, you might remember what these are. They're sort of like the precursors of relative equilibria for the n-body problem. And these are all pictures of true central configurations. So this is a crazy distribution of bodies, but the total gravitational attraction acting on each one of these bodies is proportional to the distance of every body from the center. So if I spin this guy at the right rate, it'll actually form a gravitational relative equilibria. It will be unstable, so if I perturb it, it'll fall apart. But you can also express that up to three-dimensional distributions as well. This is something that we're starting to look at in terms of see if we can leverage some of this interesting work that's going on. So that's a brief overview of the relative equilibria and how the energy and the angular momentum are actually related to each other as we go across all of these possible configurations. We can also start coming up with ways in which we can understand how or how much energy the system needs in order to actually lose particles and have things be ejected from it. To sort of line things up, 4 different numbers of bodies, 2, 3, 4, 5, and you'll see in a sec I've gone up to about 8. The first thing we want to do is to come up with all the different ways in which we could take these 3 bodies and separate them and have them escape from each other. So we can have them all together, we can have 2 of them together, 1 of them escaped, or each one of these guys can escape. And as you go up higher and higher, you get more and more of these possible configurations. And ultimately, and for each one of these, in fact, since we have finite densities, we can actually come up with necessary conditions for us to have these particles being able to escape from each other. Or we know how high we need to set the energy to have some of these disaggregations of these particles occur. I'm not going to go through this, but this sort of outlines how we can come up with these limits. And this really comes down to the fact that we can, for our finite density bodies, for any number of bodies, always identify what the minimum gravitational potential energy of that system can be. And that's sort of like the closest packing that they can have for that given number of bodies. And that leads to this picture here, which is actually it's called a Young diagram, sort of showing you all the different ways of partitioning, in this case, 8 bodies. And with each one of these partitions, we can assign an energy. And if we are above this energy, then the system can lose 1 particle, but the other remaining 7 have to be bound together. Now, they're not going to be lined up like this necessarily, but they will be bound together. Once this 8th guy leaves, these remaining guys will not have enough energy to actually escape from each other. So this actually gives us very clear levels of energy needed for understanding how we lose particles in these different systems. And we come up with these number of partitions or number of ways that these collections of bodies can actually lose additional components and have them ejected. Okay, so now we can go back to these diagrams and start to ask some larger questions about if we have this collection of Rubble particles formed in some catastrophic disruption in the past in the asteroid belt, how can they actually come together? And what is their, how does the level of angular momentum that they have actually control what sort of final configurations they can settle down into? And we can come up with a chart like this. This is for n equals 4. The first thing to note is that we have this sort of forbidden region in terms of the energy and the angular momentum. We have to have an energy above this collection of lines. It's not a single line. And along each line, we can actually identify what configurations they would have to fall into if they dissipated enough energy to get down to here. This red region, this is where we can actually lose particles. So if we start up in here, it's sort of a crapshoot whether a particle gets ejected and we go down to a 3-body system, or if the particles start hitting each other and dissipate energy and then settle down into one of these configurations. We can have these different zones where things are guaranteed to collapse down to a single body. We have zones where we could collapse to a single body or a binary system. And then we also have regions where we have, if we collapse down, we have to collapse down to a binary sort of configuration. And again, we don't need to consider ternary configurations here, because those will always ultimately be energetically unstable and could dissipate additional energy. Here it is for 5 bodies. As we go up higher, we're not tracking all of the different bifurcations that can occur, but we can still lay out what these fundamental limits are on this angular momentum energy chart as to what's going to happen with the system. And we can even take it up to n equals 6 here. And with those earlier works, we can actually go up higher and higher and higher and identify the different zones where we can lose different particles and how we could collapse down to a final stable rubble pile asteroid shape. So just to graphically, let's say we start up here in this excited region. We have 6 particles, and they're orbiting each other. Maybe they hit each other. They dissipate energy. They could collapse down, and if they have the right configuration, when they get to this point, they could actually settle into a stable configuration that looks like this. And then this would be the end of their evolution. They don't have to go through this particular configuration, however. They could actually jump over it, depending on the morphology of the system. And if they continue to hit each other and lose energy, this is like, or have some sort of a tidal dissipation, eventually, if you're in this zone here, they'd have to settle down into a configuration that looks like this. And then they can't go less than that. When they're here, they're at the bottom of the well. So this does raise an interesting question. What's the sort of probability of landing in one relative equilibria or another? And this was just a little study I did with a graduate student a few years ago, where on the 3-body diagram, we can actually identify this region where we could either end up in a stable Lagrange configuration or a stable Euler configuration. And we studied what's the probability of a randomly started collection of 3 bodies to end up in one of these 2 different configurations. This movie here, and they only dissipate energy when they hit each other. Then they dissipate energy because we give them a variable coefficient of restitution. Everything else is gravitational dynamics. This guy actually settles up and ends up in a Euler configuration, but it turns out it's a very strong function of the energy dissipation. If we have a very high coefficient of restitution so that they don't lose much energy, it sort of becomes a bit more randomized. If they have a very low coefficient of restitution, the system is sort of normalized by, in some way, it's like the target area of each one of these end states. So this also indicates that there's sort of some almost thermodynamic type of behavior going on where we don't have a guaranteed outcome of the state, but we can start to derive probabilities of which state the system ends up in. Okay, now I've mentioned escape before, where we can have a particle that actually leaves. And if you think back about, I was using this amended potential, the reality is, even though we can come up with sharp necessary conditions for escape using the amended potential, as soon as a particle escapes, this guy actually becomes kind of useless. Because if one particle escapes, we know that the total moment of inertia will go off to infinity, which means the term that has the angular momentum will actually collapse to 0. And the only thing we'll have left is just the potential energy of the remaining collection of bodies orbiting around each other. So this is not a very useful function as soon as we have something escaping. It loses all information about the total angular momentum. It's sort of useless for anything else. We can come up with a simple theorem for how we can deal with this, however. In order to do that, just one slide reminding you of Jacobi coordinates, a very convenient way of collecting n bodies together in a recursive way so that at a lower order, you don't need to worry about all the higher index bodies. But by accumulating all of these one at a time, you can build up your full n-body problem. It looks like this. This isn't quite important, so I'll just jump over this. But we were able to prove a theorem in a very recent paper where we can actually use the Jacobi coordinate, and the idea of that as the index gets higher and higher, you get to add new and additional bodies into the overall system to actually prove this very nice inequality, where we have on the left the traditional amended potential. On the right, we have the energy, and we know the amended potential has to be less than or equal to the energy. And we're able to slip in the middle here a summation of things that look like individual amended potentials, but at different orders of the system. These guys don't have all the properties of the amended potential, but definitely satisfy this rule. And the heart of the theorem is right here. And the proof is actually pretty easy. It's just algebraic. So now what we have is if a component escapes, we can always rewrite the system with our Jacobi formulation so that that last body, the nth body, is the escaping body. And it doesn't interfere with any of the lower orders, the I less than n components. If that guy escapes, then it carries away with it a certain level of angular momentum and a certain level of energy. And this angular momentum and energy is essentially lost to the surrounding space and no longer appears in the mechanics, so to speak. The picture to have here is we have these different bodies for a 6 body, and say one of them gets ejected, this guy. Then we get to sort of throw this guy away, but we have to trace the energy and angular momentum it takes with him, and that's the energy and angular momentum that the remaining system has. And the way we use this inequality is as follows. So let's say we have n+1 component system. That gives us a cap n up here. We have this amended potential. We can write the lower orders as just that summation, which stands in for the amended potential for n-1 bodies. And we have this nth one here. If this body escapes, well, the amended potential itself collapses to something that's not very useful, just involves gravitational potential energy. This term here actually collapses to 0, and if it's a single body, all of the mutual potential of that body with the remaining bodies collapses to 0. And we have this energy, though, that it takes with it, which can be identified as essentially a hyperbolic escape energy that it gets ejected from the system with. That allows us to sort of recursively redefine the amended potential with the remaining n-1 terms, and we still have the same energy inequality, but now the energy that's left for our system is systematically reduced. It depends how fast that body was ejected. So this is lost energy. Associated with this is also going to be a lost level of angular momentum that sort of puts a squeeze on our system as bodies are ejected from it. So this leads to a natural question that we also recently took a look at, which is how does this collection of n bodies, as it's ejecting some bodies, retaining other bodies, how does it actually shed this energy? How does it shed this angular momentum? Is it a very systematic approach? Is it sort of a stochastic approach or a random approach, which is what you would think? So we actually set off to take a look at that. We set up a very simple system to sort of evaluate and to understand the basics of how this happens, where we would take 3, 4, 5, 6 bodies, start them in a close to a relative equilibrium configuration, which is unstable, and then perturb them just by moving one of those components away from the relative equilibria, and we could assign a total angular momentum, a total energy to the system, and then we track the outcomes to see how much energy was lost, how much angular momentum was lost, and how that all was carried out. So again, for, say, a 6-body system, we would start it, and then we could have like a collection of 3 bodies actually escape as a group away from another set of 3 bodies. In general, a 3-body system will ultimately eject one of its members, but once it does that, it becomes a 2-body system, which then, in general, can't eject any additional bodies. And what we're really tracking is how much energy and angular momentum were left in that final system. So if we just take n equals 3 bodies, which is the simplest case, we have a sort of this characteristic curve of how much energy was lost by kicking out that one additional body, leaving a binary system, and losing that energy essentially to space. And we see that most of those guys kicked out with a relatively low energy loss, but we could have up to a pretty significant loss of energy of that system. What's sort of more interesting, and what we didn't have an intuition for, was how was the angular momentum of that leftover system distributed, and how much angular momentum was lost. And this is sort of a histogram of how much angular momentum we actually lost. And you'll see that we can lose over 100% of the angular momentum. That doesn't seem to make sense, but since angular momentum is a vector quantity, in fact, if you can actually eject a particle and have the final system actually spinning in the opposite direction, and in that case, that final system actually has lost more than 100% of the initial angular momentum. If we go up to 6 bodies, the energy loss profile is pretty consistent. Here, we had to stop some of the numerical integrations because it takes a very long time, but just tracking things, we see a very similar energy curve. although we can lose a lot more energy. And in fact, the angular momentum starts to become sort of distributed, normally distributed about this total 100% loss of angular momentum. We found that this was sort of interesting and a bit surprising. And what we're really seeing is this H sub s is the final system angular momentum once we've ejected the additional angular momentum and essentially lost that angular momentum to the background here Euclidean space. And if we characterize this angle with respect to the initial angular momentum, what we see is as we go to higher and higher values of n, that angle sort of gets uniformly or more and more uniformly distributed. So the final angular momentum that we're left with after we've ejected a number of these particles starts to become pretty much randomly distributed in space. So with this picture, we can come back to this cartoonish view of what's going on and start to understand what sort of constraints and how this whole system can evolve as it's losing excess particles, as it's dissipating energy, both through impacts and also through ejections that can occur. So here, let's say we have this n=5 body system, and we put 6 bodies in here, and let's say one of these guys gets ejected. We know the energy has to decrease. That's fundamental, and we're proving it with the previous one. We also know, however, that the angular momentum that gets left with this final one actually gets sort of randomly distributed in angular momentum, and it's not. It's more of a normal distribution. And in fact, so we lose one, and then this is the current 5-body energetic angular momentum situation. If we look at n=4 bodies and we eject another particle, we see as soon as this happens, we just get driven faster down to this fundamental minimum that we can have for this particular system. So this is essentially an effective way of understanding and starting to track how the final morphology of the system is going to depend fundamentally on what the initial angular momentum and to some extent what the energetic state of the system was. And here it loses that 4th body. It doesn't have much place to go, and in fact it has to, in this regime, has to form a binary system. It can still have some excitation, doesn't have to be at this minimum energy line, but then sort of long-term tidal interactions take over and dissipation, driving it further and further down. So these ejections can be important in constraining the morphology of the final state. We can also start to get very precise limits into how this process has to work as we increase the number of bodies in the system. And in fact, this is sort of where we're working towards next. Here's really the current work we're doing is developing ways of analyzing n-body systems when we have much more than 5, 6, 8, whatever. And what we really want to do is come up with some statistical way of interpreting the likely outcome of these different end states. A simple approach to do this is over here, where I'm applying all of our minimum energy constraints and really coming up with a phase diagram of if we have a large number of particles and we allow them to either collapse into single bodies or binary bodies, we can actually come up with sort of a phase curve, if you will, or a phase space of the different outcomes that can happen as a function of the total angular momentum of that system. And what we find are, if we have a high enough angular momentum, the only solutions that these guys can settle into are orbiting solutions. And along the bottom here, this is the mass fraction. So we can have everywhere from two equal-sized bodies orbiting each other to small bodies orbiting larger bodies. If we start to decrease the angular momentum, we have this region where we could have either orbiting or resting, what we call contact binary asteroids in this region. And if we decrease the total angular momentum more, we are completely stuck with resting or contact binary asteroids. And you might think that this seems like a bit simplistic of a picture for a natural system, but as other evidence, I'll show you a couple of pictures of the asteroid Dinkanish, which was observed by the Lucy spacecraft earlier this year with the flyby. This is their first test flyby. First thing they discovered was that this asteroid was indeed a binary asteroid. They actually had no idea. This was actually the first picture they downloaded. So I think they were pretty shocked when they saw that. And then they kept on downloading pictures, and then they were even more shocked when they got a good picture of that secondary in orbit about the primary. And in fact, and if you look at the pictures in detail, it essentially looks like what we call a contact binary. Two objects just resting on each other. I haven't given this statistic before, but it turns out that about 15% of asteroids are binary asteroids, or two guys orbiting around each other. About 30% of near-Earth asteroids are actually contact binary asteroids, where you actually have an asteroid and you can clearly see that there are two components that were formed before and are actually resting on each other. Now, I'm not saying that each one of these parts is actually a solid ball or a single ball, but they would be collections of material that then would have, through an energy dissipation process, ended up, and because it didn't have enough angular momentum, actually become a resting contact binary asteroid. So this really serves as a motivation for better understanding phase diagrams such as this. And in fact, what's going to be interesting is trying to assign probabilities of different outcomes based on sort of the relative size of these regions. And we have to make sure we do this right, but this is what we're working on right now, to come up with the probability of something settling down into an orbital situation, contact binary situation, or when it has a choice, seeing if we can come up with some way of evaluating the relative probability between those two. So this is all some current and future work. So our current focus has been on the energetics of ejection in the collapse process. Our goal is to understand constraints on forming these rubble pile asteroids, which can lead to the different morphologies that we actually see in nature, in such as shape, binarity, internal mass distribution, and the like. We've been able to do a lot analytically just by playing around with this one amended potential. So we'll probably continue to use this and see how much more mileage we can get out of this very fundamental result. We have to do some numerical experiments. As soon as we see that there's some stochasticity involved, you can't just do it analytically. You have to actually get some experimental data, if you will. And that's what we're doing these numerical experiments for. Some of the stuff that we saw was expected. I think the angular momentum distribution is probably a little bit unexpected, and that's something for us to think a little bit more about. This is a list of some of the papers over the last decade or so that have addressed various issues that I presented today. And I'll show some cool, from our simulation side of work, show you some cool movies, some former work and some current work that also form as some sort of a motivation to try to understand analytically and from a more fundamental first principles approach why we see these different sorts of interesting behaviors for these small rubble pile asteroids. So with that, I'd be happy to take a couple questions if you want.
Is there some explanation for
Pardon?
a lot of the asteroids
Oh.
spinning bulges?
Yeah,
Is there some explanation for your model?
it's probably analogous. It's different than a Maclaurin ellipsoid, but it's probably analogous to the same sort of a principle where if they spin fast, they could deform and take on a more oblate shape. There's a couple of other theories too, though. It could also be that there was an orbiting secondary that was, a pile of rubble, and maybe a planetary flyby could put it on an orbit that actually collapses onto the surface and distributes itself. Yeah, yeah. Another interesting aspect, which we didn't even talk about, is a lot of times with those bulges, at the edge of that bulge, it's actually a zero gravity situation where centripetal acceleration tends to balance the total gravitational attraction. So these objects are actually very much on the edge, if you will. And material wants to naturally flow downhill to get to that equator. If it gets there, though, it just flies off. So it's sort of an interesting situation. Yeah, that alignment gets randomized, really. Yeah, because when we were looking at that angle, that was, it started to go more and more flat. Yeah. Yeah, but we didn't have an intuition for that. For these few, caveats, few particle, we don't have any of the other stabilizing gas drag or other sorts of effects that people talk about when you get into a planetary disk. Yeah, yeah.
Yeah, so you're looking at self-gravitating
Mm-hmm.
solar system. How small does the thing for tidal have a much effect than self-gravitating?
Yeah, that's actually relatively scale invariant, and you have to be in rule of thumb, and it depends on the density. Okay, but density is around 1 to 3. You have to be like 10, 30 times the radius of the body away before the solar tide actually takes over and clearly dominates. So there's a pretty large region where these guys are just playing with themselves, so to speak. That might be interesting. I certainly haven't thought about that, just because stars are big and I'm just dealing with little rocks. The big difference is, and I'm sure that there can be stellar impacts and stellar mergers and all that, but the probability of those are probably much less than when we have these finite density bodies and they just get in the way of each other and they smack into each other. So fundamentally, I think the physics is going to be a little bit different when you go up to the galactic domain. Yeah. Yeah, that's a good question, and actually it goes back to this diagram actually. And it really depends on what that initial energy level was. If the energy is high enough, basically you could have any of these guys at a lower energy as a possible outcome of that ejection. But if we're at -5 energy, you couldn't have one of these situations occur. So it really depends on how much energy is initially in this collection that we're starting to look at.
One more question. You mentioned a number of historical guys, Euler, DeGraaff, of course, one who's even more historical is Bode, B-O-D. Do you feel Bode's law is just an accident? Because space is a planet, asteroid, pseudo-planet.
You're talking about the Titius-Bode law?
Yeah.
That's like this interesting situation. I don't really have a strong opinion on it. There is a journal, Icarus, that strictly forbids anyone talking about the Titius-Bode law in any paper that they submit to it. So I know it's certainly controversial. I would think with the plethora of exoplanets, if there is some sort of systematic